Okay, welcome to 9.3, the end of Chapter 9. We're going to turn our attention now to independent samples for two means. We're going to compare two different populations. So remember that we need to be able to identify when samples are independent, and if they are independent, we'll follow the methods in this section. The only difference with independent t-tests is that there's two different formulas, and that depends on assumptions that we can make about the population variances. For us, that's not going to be a big deal, but when you're working through the text, make sure that, well, I would recommend that you watch this first so that you can see how those two different tests relate. We're going to start with hypothesis tests. This is a two-sample t-test in our calculator. The variables and parameters are exactly what you'd expect. Two random variables for the two different populations and two population means. The hypothesis, the null hypothesis, is that there's nothing different between the two populations. They are the same. So we saw that previously in the previous section, and we're seeing that again here. Notice we don't need to form a difference because we will be talking about two different independent populations. Now, as always, our alternative hypothesis is one of three flavors. We could have that the first population mean is less than the second, or simply that they're not the same, or that the first is larger than the second. Any of those could be our alternative hypothesis. The assumptions, there are four of them. We need simple random samples, and we like it when the sizes of each are equal. So not something that we will worry about too much in this class, but that is an issue out there. For us, we're simply going to get sample sizes that are about the same. Remember, there's two usages of the word independent. And in this second case, the two samples are independent. Basically is ensuring that we are not surveying or measuring the same members of two different populations, that they're independent in the sense that they don't overlap. And of course, we need to show that we have normally distributed populations. So the way that we can get that is either because the sample size is greater than or equal to 30, or because the populations are known to be normally distributed to begin with. Now, this is new, and this is a word that will follow us throughout 9.3, and that is pooling. So if the population variances, now we say variances in 9.3. We didn't say variances before. We say variances now because we are going to use the variances in the test to see if we have to pool or not. That's not going to be an issue for us, as I've said before. We're going to work through this in the way that's easiest for our calculators. So pooling becomes an issue. So if the population variances are known to be equal, then we can pool the sample standard deviations. Otherwise, we do not pool the sample standard deviations. And if you're looking at that thinking to yourself, how often are we going to know the population variances, let alone the fact that they're equal? And you're right, that does not happen very often. So more often than not, in this last assumption that we're making, we're going to not pool. So in our calculator, we're going to say, no, don't pool. So the sample statistic, the test statistic, and the degrees of freedom, remember these are t-tests because of what we were just talking about, the standard deviations. The t-test comes to us in a formula, and it is related to a degree of freedom that's found in a table. You've got that in the table I handed out the last day of class. The p-value is based on the alternative hypothesis. So it's either a left, right, or two-tailed test, and that depends on what it is that we are testing. And I don't know if I've said this recently or if I've said this in the videos, but it's useful to remind yourself that the p-value is a probability. It's the probability of getting results as extreme as the sample while assuming the null hypothesis. Part of the power of hypothesis testing is that we can assume what we're trying to show isn't true. We can assume the given information in the null hypothesis and say, well, if that's true, what would the probability be of getting the results that we did in the sample? As extreme means that we're taking into consideration which side of the normal curve we're looking at, the right tail, left tail, or both. And then the conclusion, this is copied and pasted as always, so there's a reminder that nothing new's here. If the p-value is less than alpha, we reject the null hypothesis. Otherwise, there is not enough evidence to support the alternative hypothesis. And the interpretation, that's where we say as clearly as possible in clear English what that means. Okay, so let's look at an example. It says that the cholesterol level of patients who had heart attacks was measured 2 days after the heart attack. The researchers wanted to see if patients who have heart attacks have higher cholesterol levels than healthy people. So they also measured the cholesterol level of healthy adults who show no signs of heart disease. Does the data show that people who have had heart attacks have higher cholesterol levels over patients that have not had heart attacks? Test at the 1% level. And this is similar data to what we used before, so if that looks familiar to you, that's because it is. I'm going to scroll down, show you the whole thing. You've got this in the workbook, of course. The new data is in the corner down here. So if you still have that data in your calculator, just put that new data in. In fact, the healthy individual data may be entirely new unless you've been working through the examples and the text, in which case you've already got the cholesterol level data for healthy individuals. But compared with the data that we used in 9.2, you'll need to add 2 new cholesterol level for heart attack patients. That's the 228 and the 235, if you want to get the same results that I'm getting out of the calculator. So we're going to take a look at our calculator. This works out really nicely. This is a 2-sample t-test. So when we go into our calculator, we're going to go over to tests and a 2-sample t-test, and then we're going to enter the data from list 1 and list 4. The reason those 2 lists look so odd, or at least not adjacent, is because we put in list 1 for the cholesterol level of patients 2 days after a heart attack, and then list 2 was 4 days after, and then list 3 was the difference. So list 4 is the new data for healthy individuals. We don't have to make any differences here. These are 2 independent populations. The frequencies are 1, and we are testing the claim that the first mean, that is mu sub 1, is greater than mu sub 2. That is that the cholesterol level of heart attack patients is higher than the cholesterol level of healthy individuals. And then underneath that you'll see a new question. And this is the easy way out. It's easy for us but hard for our calculators. Because we can simply say, no, don't pull these results. Use the formulas when we cannot make any claims about the population variances. And that makes this a lot more mechanically difficult for the calculator, but it doesn't make it any more difficult for us. So we're simply going to say no. Now, when we do that, we get some great data out of our calculator, as you'd expect. A nice reminder of the alternative hypothesis, so that should match perfectly with what you were asked to test. There's our t-value, and my golly gosh, that's fairly high. This isn't exactly standard deviations, but we can think of it in the same kind of way. That's about 5, 6, 5 3/4 standard deviations away from the mean. That's a long way. And when you look at that p-value, we see that that is almost 0. That's essentially 0. There's our degrees of freedom and our 2 sample means, x bar sub 1 and x bar sub 2. So that's information that we will report as well. This is one of those screens on your calculator that has a little arrow. So if you need to, you can always scroll down and see some more. So when I did that, I got some more information. I got the sample standard deviations and the number of each sample size, so n sub 1 and n sub 2. That's a nice way to ensure that we entered all the data that we were supposed to. A note about pooling. So we are going to say no, and that's because we are not doing any tests yet about the variances, about the population standard deviations. Okay, we're on the next page and we're working through the hypothesis test itself. The first thing is the random variables and the parameters. So the first thing I see is the cholesterol level of a heart attack patient. So that's going to be our random variable x sub 1. X sub 2 is the cholesterol level of healthy individuals. We're doing a t-test. We're talking about population means. So our parameters, remember parameters come from populations, is mu sub 1, the mean cholesterol level of all heart attack patients, and mu sub 2, the mean cholesterol level of all healthy individuals. Our hypothesis test, well, the null hypothesis is exactly what you'd expect. That is, there's nothing to see. The two populations have the exact same mean, or at least within the level of statistical significance. The alternative hypothesis is what we were asked to test. We were asked to test the claim that that first population, mu sub 1, that's the population of folks who've suffered a heart attack, their cholesterol level is greater than those folks who didn't show any sign of heart disease. And a reminder of alpha, our level of significance. Alpha is 1%, 0.01. Our assumptions, and you may be kind of feeling uncomfortable at this point because nothing about this said that those samples were random. And so we say that. Perhaps this is a unique set of samples. We don't know. The next thing that we need to say is that new usage of the word independent, and that comes to us from the fact that these are in fact different populations. In other words, you either have no sign of suffering from heart disease or you've had a heart attack. We also need to say something about being normally distributed. And just like before, we're going to say that cholesterol levels are known to be normally distributed. So that works out nicely for us. And last but not least, we have to make sure that we're doing the correct test, that we're actually doing what we're supposed to be doing. So we're doing this test. We're saying that, honestly, we don't know anything about the population standard deviations. You can say that in exactly the same way by saying we don't know anything about the population variance. And because of that, we will not pool. So that was the no that we selected on the calculator screen when we were using the calculator. Now the calculator told us a bunch of good stuff. It told us the sample statistics. That is the mean of the two samples. That first sample were folks who'd suffered heart attacks. And the second sample is healthy individuals. And notice that the sample means do differ. Now, without knowing the standard deviation, it's difficult to know how significant that is. So our calculator is doing a lot of work for us when we say do not pool. We don't know anything about the relationship of these two standard deviations. And it's given us some good information. So this is just recopied from that calculator screenshots on the previous page. So there's our t-value and there's our p-value. So the conclusion, well, that p-value is much smaller than alpha. So we are going to reject the null hypothesis. And we can say that nicely. There is sufficient evidence to say that healthy individuals have lower cholesterol levels than heart attack patients. Now that's all very well and good, but you might ask yourself, how much less? What is the difference in the cholesterol levels? And to do that, we'll answer that question with a confidence interval. On our calculator, that's a 2-sample t-interval. Steps 1 and 3 are the same as what we saw before, so then we start with step 3, the new step 3. Our confidence interval, this is just copied and pasted from before. It's our point estimate plus or minus the margin of error. And our point estimate, well, the thing that we know about is the two sample means. So we're simply going to say what the difference in the sample means is. Now the margin of error comes from multiplying our t-score by that standard error there. And that comes from either using Bell or some sophisticated tables that are also out there. And either of those will work. So the confidence interval, and this is just restating what we've said before, we're making claims about the difference in the population means by how much one is bigger or smaller than the other. So we're simply going to take that point estimate, the difference in the sample means. We're going to subtract the margin of error to get our left endpoint. That's going to bound our population mean difference, and then we'll add the error to get our right endpoint. And of course, that E comes from T, and T is the bridge between our confidence level and the margin of error. So T is the thing that connects C to E. So like our previous example, we've got all that in our calculators, which is great because it makes it so much easier to find the confidence interval for that data. It says to use the data that we did previously. It says find a 90% confidence interval for the mean difference in cholesterol levels between heart attack patients and healthy individuals. So this is a two-sample T interval. So we'll go into the stats menu and over to tests. And we're going to use the data. We've got it in lists 1 and lists 2. Our confidence level is 99%. So we're going to enter that as 0.99. And then easy for us, hard for our calculators, is to simply say, no, don't pool it. We don't know enough about this data to make that claim. And not long after that, we get our confidence interval. And there it is, 30.064 to 82.24. And then the degrees of freedom and the means of the two samples, the standard deviations of the two samples. And there's more. That downward pointing arrow tells me that I've also got my two n's. Okay, so let's actually perform a hypothesis test. Steps 1 and 3 are the same. They become steps 1 and 2. The new step 3 is to state our sample statistics and the confidence interval. So here's our sample means. That came out of the calculator. And here is our confidence interval. So just recopied from the calculator screen. And of course, our confidence level is 99%. The statistical interpretation is when we say that there is a 99% chance that that interval between 30.064 milligrams per deciliter and 82.24 milligrams per deciliter contains the true difference in population means. Now, look at this in clearer English, and it's actually pretty interesting. The average cholesterol level of a heart attack patient is between 30 milligrams per deciliter and 82 milligrams per deciliter, more than the average cholesterol level of a healthy individual. Now in the book there's a lot of discussion as part of the hypothesis test and the confidence interval about when to pool and when not to pool. So what I've done is a little bit different. I've moved all of that discussion to this last page of our workbook and talk about it in one place. I'm going to say right at the beginning that you can get reasonably good answers by always saying no to your calculator when it asks to pool or not. But let's talk about this just so that the rest of that discussion in the book makes a little sense. First off, we are assuming that the two population variances are not equal. That's what's allowing us to say that we should not pool those results. And so you might say to yourself, well, what would happen if the population variances were equal? And the advantage there is that there's a simpler method of finding the t-score and the margin of error. And your response to that may be that that's just a matter of how much work the calculator does, and I'd have to agree with you. The problem, of course, is we don't know the population variances. We only know the sample variance, and not the population variance. So if we want to use the simpler method, we first have to show that the population variances are equal. And there's a way to do this. No great surprise. And it is a brand new test. It's an F-test. So to do that, we have to show that the variances are equal. That means that the ratio of the sample variances is not unusual. So to do that, we have to ask this question, and that is if the probability that the F score is greater than the ratio of the variances, and if that probability is greater than or equal to 5%. I've stated this two different ways because the larger of the two variances has to be in the numerator. So the larger of the two has to be upstairs. And you can do a F-test in your calculator. It's F of the cumulative distribution function, and then you have to put in the degrees of freedom, and you have to put in that upper bound. So that allows us to use a simpler formula. And beginning on page 324 in our text, she shows you how to use that simpler formula. And here they are. So here are the t and the t-test for the hypothesis test, and the error for the confidence interval. And you'd have to agree that those are a little bit simpler.